Welcome to Project 2.9, the 595 Shift Register Unpacked, a hands-on exploration of digital memory. In this project, we'll build an 8-bit serial-in, parallel-out shift register entirely from scratch, using D-type flip-flop ICs and AND gates. No shortcuts, just logic. A shift register is a digital circuit that stores and moves data using flip-flops, simple memory elements that store 1 bit each. Each clock pulse moves the data one step through the chain of flip-flops. The 74HC74 IC we use here includes 2 D flip-flops. By connecting 4 of these ICs, we can store and shift 8 bits. The shifting is done using a nature of the 74HC74 SN chip, that whenever the clock is on the rising edge, it reads the data pin or the D input pin of the chip and makes that its output. It latches on to the input, remembers it, and makes it the output. By connecting 8 chips in a row, we make each output the input of the next chip, and we connect all our clocks together. Whenever we press the clock button, each chip takes the output of the previous chip and makes it its output, therefore moving the bit down 1 or shifting it down 1. The 3 buttons located in the top left of this circuit are the clear button, the data button, and the clock button in order. In this shift register project, each button in the circuit uses either a pull-up or a pull-down resistor to ensure reliable digital logic levels and prevent floating inputs. The clear button is connected to the CLR or clear pins of all the flip-flops and uses a pull-up resistor. This keeps the CLR pins high by default or the inactive state, and when the button is pressed in the active state, it pulls the line low to reset all outputs to 0. The data button, which inputs binary 1s or 0s into the first flip-flop, uses a pull-down resistor to keep the data line low when the button is not pressed, or the inactive state, ensuring a clear 0 input unless intentionally triggered. Similarly, the clock button, which advances the bits through the flip-flops, uses a pull-down resistor to maintain a stable low state when idle, avoiding accidental clocking. Finally, the latch button, or latch switch, which enables the parallel output through the AND gates, also uses a pull-down resistor so that the latch signal remains low until the button is deliberately pressed or the switch is deliberately switched. This is important so that it only latches the information and displays it when the user wants to. These resistors are critical for preventing erratic behavior due to floating or undefined voltage levels on digital inputs. This is the final circuit working in both Falstad simulation and in real life. Thank you for watching my 2.9 Unpacked 595 shift register video.